Thank you very much. So I actually been skiing to Senja and to Lyngen the last two years, and that's been really pleasant. So I'm going to talk about networking for AI. I've seen there's been a lot of AI-generated pictures today, so that's not what we're going to talk about. We're going to look under the hood to see actually how do we connect all the GPUs? How do we get that work? What are the challenges? How can we scale it from 1,000 to 10,000 to 100,000 of GPUs in a cluster? So in a standard data center network, there are 10,000 of flows, quite small, based on TCP, UDP, quite easy to load balance across multiple uplinks, the spines, and the leaves. The AI fabric work completely different. The GPUs do their work, their calculations, and when they're going to, to exchange the metrics, there are large flows, there are elephant flows, there are consistent flows. All GPUs exchange the metrics with each other at the same time, which actually blasted the network. It goes from 0 to 100 in milliseconds. So there are definitely different requirements on building an AI network. There's also a term called time spent in network when talking about an AI job. Apart from all the calculations that happen on the GPU side, the time that is spent in the network is measured. We normally say, depends on the AI workload, but the average is about 10 to 20% that actually an AI job is spending exchanging the information between the GPUs. So let's kick off. I'm going to talk about the networking basics, the challenges we have, how to build scale-out AI networks, and also talk about Ultra Ethernet. And then we have some questions and hopefully answers. Today, or until today, we have built an AI backend network based on mostly on InfiniBand, and the front-end network was based on Ethernet. The challenge for many companies in this case, they have two different networks to operate, the two teams, different tools, different challenges. So that's quite of a siloed way of building networks. Wrong. So what we're talking about today is the AI fabric, where we can use Ethernet both for the backend network, which is basically the GPUs connecting to each other, exchanging all the information, and the front-end network, where we host our storage, our applications, our Kubernetes, and all of that stuff. So we're creating a unified fabric, so we can use the same tools for managing and monitoring the both networks. We can use the same telemetry for both networks. We can do automation in the same way. So we become definitely more efficient by doing it this way. So you all heard about GPUs. There's been some talk about GPUs today. Down to the right, we have an H100 from NVIDIA, which is a typical XPU server, GPU server. It has in total 8 GPUs. And there are actually 3 networks we talk about when designing a AI backend network. We have the CPU and storage ports that's connecting to the front-end network. In the front-end network, the standard data center is often where the storage is hosted for the AI. We have the GPU ports, normally 8 times 400, which means 400 per GPU, connecting to the backend network, where all all data between the GPUs are exchanged. Then we have an internal network between the GPUs. So there is an internal matrix or bus or what do you call it? In NVIDIA language, it's called NVLink or NVSwitch, depending if it's in one server or in a rack. So those are the 3 networks that we need to take into account when we do designing AI networks. Any questions? There are also different kind of topologies we can use when building the AI network. We have the standard layer 3 leaf and spine, the same topology that we use in our standard data centers based on IP. And we have what we call a rail. In the layer 3 leaf and spine, you connect all the GPUs in one rack to a leaf switch, and then they are connected to the spine, which means all GPUs can communicate over the IP fabric with each other. With a rail only, each GPU 0 in each server connects to one leaf switch. GPU 1 connects to another leaf switch. So that's actually what's called they become a rail and have the same rank in the GPUs. And for them to communicate, if GPU 0 in a rail, for example, should talk to another GPU 0, they just have one hop through a leaf switch. They are connected to the same leaf. But if GPU 0, for example, should talk to GPU 7 on another server, they will go to the GPU 0 on that server and then use the internal network to go to the GPU 7. So there are pros and cons with both. If you have a small installation, rail works well, but if you need to scale it above 500,000 GPUs, the leaf and spine are definitely more flexible to scale out and connect more GPUs to that one. So what are the challenges when designing a Ethernet backend network for AI? We talked about the different domains. It's more from an operational point of view. We talked about that endpoints are fast and they're blasting the network. Then we have the two blue ones that I'm going to talk about is more or less about how to do load balancing. And that job completion time is really important because the slowest job dictate the total time for that AI job to complete. Power and cooling is, of course, interesting. We talked about optics. In those kind of environments, we normally have like 10,000 optics. So the lower power each optic have, it's really important. And also talked about the observability and visibility. How can we catch microbursts from this environment and to start troubleshooting if there is issues? But let's have a look on the load balancing part. In a leaf and spine environment, we're using ECMP as a standard load balancing, equal cost multipath. So it actually hashes each flow, and that works very well when you have 10,000 and 100,000 of smaller flows. But if you have elephant flows with a low entropy, which is basically low numbers to actually do the hashing on, it's easy to place the same flow on two flows on the same link and start to have collisions. We have ECN and we have PFC to protect the network and have the senders to slow down, but we don't want to use that too much because that will impact the job completion time. So standard ECMP is not good enough for AI workloads. What was developed after that is basically that we used RDMA-aware static hashing. We looked a little bit into the InfiniBand frame to be better to be able to hash it better, but it's still static hashing. It has no awareness of the link utilization or the buffers of the switch. Then we introduced dynamic load balancing, which is much more better because then we measure the buffers, the link utilization, and can place flows on the lowest utilized links. But dynamic load balancing is still per switch. It has no understanding of the leaf and spine topology. Because if it places it on the link that is good, the next switch can have overutilized links. So the next thing is cluster load balancing, which is basically topology aware. So it can identify the collectives, which are the AI jobs, understand the collectives, and understand the network topology, and basically place the flows all the way from A to A or B to B in different paths, or the least utilized paths in the network. Is that good enough? Yes, we've installed a couple of solutions with both DLB and CLB, and it works. But I will talk a little about Ultra Ethernet, which will solve a lot of those issues. So when we look at the AI backend design, there are some design principles to think of. Symmetric is critical. Hosts, which is GPUs, should be equally distributed across all leaf switches. Every leaf should connect with the same amount of uplinks to the spines. When you start building an AI backend network, the spine layer should be fully built out from the start. And then you can add leaves and GPUs later if you want to scale that out. Why? Because otherwise you need to start recabling everything, and that's not funny when you have thousands of fibers. One important thing, no oversubscription between leaf and spines, which means the number of terabits coming in from the GPUs to a leaf switch, the number of terabits bandwidth you should have out from the leaf switch to the spines. So those are the platforms that we are using when we are building AI networks, the backend networks. A fixed platform with either 32 or 64 times 800 gig, or the chassis that can have up to 576 800 gigs. Sorry. We talk about different tiers when we need to scale the AI backend network. The simplest one is to have a single tier where you put the switch in the middle and the GPUs on the side and just connect it into the spline. We can have up to 1152 GPUs connected to the same switch. If you want to go higher, you need to start building a two-tier model where you have the leaf switches connecting to the GPUs, and then the leaves are connected to the spines. So we have every GPU can talk to every GPU in the cluster. And then we have the three-tier model where you're building pods with 2 tiers and then connect them into super spine. And then you can scale really high, over 200,000 GPUs. So let's have a closer look on the, it's lacking. So this is absolutely the simplest configuration and installation of a AI backend. You have a chassis with line cards, can support up to 1152 400 gigs GPUs. There's a minimal amount of configuration and tuning that you need to do, have it to perform. And it's a lossless schedule. It's a lossless architecture built into the chassis. So this is the simplest configuration that we have. And you can actually grow this by scale also. You don't need to, if you're only going to use 400 GPUs to start with, you just buy line cards that supports the number of GPUs you want. Then you can add line cards to that one. And if you want to start really small, you can, of course, use a 64-port fixed switch in the middle also. and then you can have up to 128 GPUs connected to that one. For the next step, we have the two-tier backend. It's also quite easy to build because it requires a little bit more tuning around ECN and load balancing than the tier 1 does. But you build out your spine layer to keep this fully build out your spine layer from start, and then you can add leaf switches when you need to scale. So with this one, we can scale up to 8,000 GPUs in the same cluster. And when that is not enough, we need to look at the, we really don't need to look at the 3-tier model, but what you can do to scale a layer 2 or a tier 2-tier model is basically you can use the chassis in the spines, which means you can add more leaves, and then you can grow your, you can easily grow your fabric up to almost 100,000 GPUs. To summarize, most AI clusters can be built with a 2-tier design. We have the one with the chassis, the 2-tier model with the chassis, and fixed switches. We scale up to 74K of GPUs. If you only want to go with the fixed switches, we can scale up to 8,000 GPUs. If you're only building with a 2-tier fabric with chassis, you can go over 500,000 GPUs in the same cluster. Why? Isn't that green also? That's very costly. So it's a bit of a TCO part included here also. So looking not in the future, actually the specification for Ultra Ethernet 1.0 was released a couple months ago. What is Ultra Ethernet? Ultra Ethernet Consortium was founded in 2023 by 12 companies. Today there are 100 members, 1,300 participants, and the mission is to actually create Ethernet and the Ethernet fabric to handle mission-critical AI and HPC workloads at large scale. So we can see the companies that are there are the semiconductors, AMD, Intel, NVIDIA, the hyperscalers, which have the largest installations in the world, Meta, Microsoft, and Oracle, and the networking companies like us, Cisco, HP, Juniper. So it's a collective effort from the industry to do to standard on Ethernet for the AI workloads. Taking one step back, today we're transporting RDMA from the sender of the of the metrics. We use redirect memory access, just to be clear about that, and transport RDMA frames over Ethernet by using Rocky V2. Basically, we take the InfiniBand packet, put a UDP header on, put an IP header on, and an Ethernet header on. So this is the transport protocol that are used today for Ethernet. So Ultra Ethernet Consortium is not about hardware, it's about software. It includes the full stack, from the NICs to the links to the transport layer and so on. So in the first draft, there is a new transport protocol called Ultra Ethernet Transport that will be replacing Rocky V2 and InfiniBand. So this will run on IPv4 and IPv6. It's designed for really large scale, so it will take advantage of what's existing today, the addressing, the routing, etc., in the fabric. But what it adds is actually multipathing RMA. It supports packet spraying, which makes it much more easier to load balance. Relaxed delivery ordering. Packet can arrive to the destination host unordered. We don't need to reassemble the packet before sending it out to the host. Rapid loss recovery, new congestion algorithms to control for the data centers. If we take a bit look on the transport protocol, the packet spraying. So what's happening is basically the packet spraying is not from the networking part. It's introduced from the NIC itself on the GPU. So instead of sending a flow, it sends a lot of packets with different UDP header number, UDP ports. So we can load balancing each packet over the leaf and spine fabric. And while they don't need to arrive in order, and how can that be achieved? Yes, because from the sender GPU, it adds a tag directly to the memory of the destination host. So when a packet arrives, the destination host places it directly into the memory. And when we can do packet spraying without reordering the packet, that will increase the throughput in the network. And why we don't need to reorder the packet in the network, that will lower the latency. So this feature will lower the latency and increase the throughput in an AI backend network. I would like to share some customer designs that we have done in the Nordics. Some of the customers. I've chosen one of each model. So for a company developing software for self-driving cars, they run their own cluster. They have chosen a single-tier design, and they have up to 576 400 gigs GPUs. And they use it for their own purpose, training models. Customer number 2, which is a sovereign European cloud based out of Sweden called Everock. They've started with the same design for their testing. Now we're looking into a 2-tier design based on fixed switches. They will initially start with 1,152 GPUs in the cluster, and they'd like to scale it above 4,000 GPUs. And they will actually sell GPU as a service to customers. Interesting, because then security suddenly comes in. You don't want to run your backend data and share it. How about encryption? About segmentation in the AI backend between the customers? So that's also why we need to use layer 3 in the backend to do VRFs and so on. Customer number 3, it's a global cloud provider with a data center in Luleå in Sweden. They have over 30,000 GPUs connected in the same cluster. They are using a 3-tier model. They use it only for their own training, and they create great pictures. So that was all from me when it comes about the AI, building AI networks. Just a short one. We have an event 21st of October in Oslo. You are very welcome to attend. Talk to me, Andreas or Jacob, and we'll share information about that. And now to the questions and hopefully answers. No questions? Have any one of you been involved in building, thinking, designing an GPU cluster or AI cluster? Good. One shy guy in the back. So, yes, please.
I can fix the microphone.
Thank you. And it's around the load balancing.
Yeah.
You mentioned that you have tried cluster load balancing and it's working well, but it needs to be topology aware, right?
Yeah, yeah.
What are the main challenges that you have seen that by being topology aware? Is that something that needs to run on the switches? Every switch needs to be aware of that? Is an external controller? How that normally works?
Very good question. It's actually a piece of an agent that is running on every switch, and there is a controller piece of that. We have it built into in our solution to our management system that it takes care of that, and then program the switches. But as you say, it's today based on a controller solution. So
Okay. And my second question to that, talking about observability, is that data accessible? Because one of the few things that it would be pretty good, especially for tier 3 type of networks, is how you want to leverage and want to see maybe create some kind of scoring system around your different layers and verify burstiness, load balancing, and so on. So just want to check if that data is accessible, is exposable, or are there plans to expose it?
repeat the question.
So it's around metrics, basically.
Yeah.
Metrics around that data, the load balancing. So these agents have that capability of doing the load balancing. I would imagine that they have also a lot of data around metrics of how that load balancing is working. And my question is, how is that data? Is that data now exposed in the controller, or are there plans to expose
Yeah.
it?
It's exposed in another way because we're using streaming telemetry, and we measure microbursts in our switches. So we can see when there is a microburst on an interface, and we also have a piece of software that can run on the GPU NIC itself. So we can see which NIC is impacted by the congestion, so to say, which flows from that NIC are impacted, and what path it takes through the network. So
Awesome. The last question, and I promise this is the last one, is
we'll have a chat over the beer later, but come on. Hang
well,
with.
the last one would be, are you using some kind of open telemetry to expose that data, or GNMI or telemetry that allowed?
We have our own, we're streaming all the telemetry directly from, as soon as there is a MAC change or a route change, we're streaming all that telemetry to our own solution from a specific agent running on the switch called Terminator. But we have support, of course, for GNMI and so on. So
is Terminator the
Terminator agent that's running on
that
the
is running. Oh, okay, awesome.
EOS.
Thank you.
Not to be too Arista specific. Thanks for your questions.
Right. Any other questions?
I'm running out of time. So
yes. All right. Thank you very much, Henric.
Thank you.